Hello friends, welcome to my channel Chemistry with DB. In this video, I'm going to explain the chelate effect aspect involving transition metals, and this involves monodentate, bidentate and multidentate complex ions. I hope you understand these three different types of complex ions. If not, I'll create another video to explain just that. Now, we need to understand as to what is chelate effect, because there are lots of exam questions which are asked on this topic. Now, chelate effect is a reaction in which a bidentate or a multidentate ligand substitutes a monodentate ligand from a monodentate complex ion, or a multidentate ligand substitutes a bidentate ligand from a bidentate complex ion. This reaction is thermodynamically very feasible, whether we look at it in terms of the entropy, which is delta S, or free energy change, which is delta G. Now we need to understand the explanation for this one as to how we can explain in terms of entropy or free energy change. Now we know that the equation for the free energy change is delta G is equal to delta H minus T delta S, wherein delta G is the free energy change, delta H is the enthalpy change, and delta S is entropy change. Now let's look into an example involving feasibility of a reaction wherein a monodentate hexaquaferrate 2+ ion is reacting with a hexadentate ligand EDTA. What happens is that EDTA substitutes all of the water ligands from the monodentate ligand, and those 6 water ligands are released, and it forms a multidentate complex which is ion with EDTA. Now let's look into as to how this one is thermodynamically feasible. Now delta G is equal to delta H minus D delta S, and for feasibility we know that delta G should be less than 0 or negative. In this reaction, enthalpy change delta H is always going to be 0, because delta H is what? Delta H is bond breaking minus bond forming. Energy needed for bonds breaking and energy released on bond formation. It's the difference of these two which is the enthalpy change. Now why is this 0 over here? Because as you can see that there are 6 coordinate bonds being broken here that water ligands had formed with ion, and it's the 6 coordinate bonds that EDTA has formed again. Those are also coordinate bonds. So 6 coordinate bonds breaking and 6 coordinate bonds forming. So therefore virtually there is hardly any enthalpy change. That's why I'm saying that enthalpy change here is approximately 0. Entropy change delta S on the other hand is positive. Why? Because that depends on the number of particles in a particular reaction. Here we can see that 2 reactant particles are giving us 7 product particles. So as a result of this, number of particles increasing means greater disorder, and therefore delta S is positive. Now delta H is 0 and T delta minus T delta S is a negative figure. As a result of this, what will happen is that delta G is going to be negative, always negative, and therefore the reaction is going to be feasible. Now let's take another example looking into the feasibility of a reaction wherein a bidentate complex gives rise to a multidentate complex. Here we are looking at the ethyl diamine ligands which are bidentate, which is giving you a complex with Cu2+ ions. What happens is when this bidentate complex reacts with EDTA, which is a hexadentate ligand, then EDTA again drives out all of the ethyl diamine ligands from here, giving rise to CuEDTA2-, and the 3 ethyl diamine ligands are substituted. In a nutshell, what's happening here is at a bidentate complex is giving us a multidentate complex. Now let's look at it again in terms of free energy change. Here delta G again is equal to delta H minus D delta S. Delta S here, or the entropy change here, is positive because there were 2 reactant particles here which gave rise to 4 product particles. The number of particles increasing means there is greater disorder in the system. Delta H on the other hand is again approximately 0 because it's the 6 coordinate bonds being broken and 6 coordinate bonds being formed here. Therefore, delta H is 0 and minus T delta S being negative. Therefore, delta G is always negative, and therefore reaction is feasible because delta G for feasibility has to be less than 0 or negative. I hope you like this video, and if you like it, then please like, share and subscribe. Thanks for watching this. I look forward to seeing you in my next video. Take care. Bye.